with Volker Springel, who will tell us about exploring cosmic structure formation with hydrodynamic simulations, past, present, and future.
Yeah, thanks a lot. It's a real pleasure to be here back at the ITC. Of course, the ITC had a huge impact on my own career because I spent a postdoc here in the early 2000s, and it has actually ever since impacted my work. And I do think the ITC is probably a uniquely important place and institution for, especially for the field of numerical galaxy formation, where many of the techniques have been invented. And I think the field has really been advanced at the leading edge for several decades already. And computing was an important factor in this. And here you see a famous computer coming out of Harvard Mark I in the 40s, one of the first supercomputers. Mako, important supercomputer, not so well known, but very well known to me, in the basement of the CFA, built up by Lars' group, together with several other machines in the early 2000s. And that's actually what we used at the time to make cutting-edge calculations. Nowadays, of course, the field has moved on to even bigger machines, and we'll also get back to this topic later on. Now, cosmology, as you know, of course, we have a miraculously good idea about the initial conditions. And so the idea of hydrodynamical simulation of galaxy formation is very simple and very compelling. Just take these initial conditions, evolve them forward in time, and if you account for all the astrophysics properly, you should get out the galaxies we see around us. And that research program is basically what this field tries to do. But it's evident that this is very difficult, right? There's lots of complex astrophysics. And you would like to make the stars and also understand how the star formation is regulated. When you make galaxies, you also want to understand the role of black holes play. So that's a huge difficulty in this naive research program, I would say. That's also why 20 years ago, and I will talk now a little bit about the past and the situation that we faced at this sort of beginning of the ITC, and the situation wasn't really good because really, the people tried already to do cosmological simulation of galaxy formation, but the outcome was largely a significant failure. There was a term called cooling catastrophe, describing the fact that all the galaxies overproduced the amount of stars by huge factors, even at very poor resolution. And despite attempts to include feedback processes from supernovae by thermal energy injection, that failed to regulate star formation galaxies. And evidently the resolution was also fairly poor, and even to theorists it was known the ISM is multiphase, and we tried to ignore this for a long time, but it was problematic to make progress. There was really an impasse in the field at the time. And in my joint work with Lars that we started at the CFA and then the ITC together, we addressed this initially with basically two ideas. One was to introduce an explicit subgrid model for the ISM to basically acknowledge the fact that we cannot yet resolve the multiphase ISM, and in addition, acknowledge the fact that the dynamic range of the real universe is so large, we don't have enough resolution elements in any calculation we can possibly do to simulate this properly, all the galaxies in the different sizes. So we did address this by coming up with the idea to do a comprehensive set of calculations on different scales. And I'll show you this. And both of these ideas, they actually have stuck on, and they are still in use, to my surprise, even today in the field. So this subgrid model, had a simple analytic underpinning, but the idea was to come up basically with a modified effective pressure law for the unresolved ISM that would regulate how star formation is happening there. And with this, you could then make predictions for the star formation rate density, say in spiral galaxies as a function of the gas surface density. And the consumption timescale of gas would be adjusted to reproduce observational empirical facts like the Kennecat star formation law. And with that, you could then start simulating suddenly galaxies. We got then spiral galaxies that behaved reasonable. And we used this idea to run calculations on different scales, different box sizes, from 1 megaparsec to 100 megaparsec. You see here graphical the picture of these calculation set. For each of these boxes, we did do resolution studies as well. And we did this on this Mako computer here at the CFA in the basement. And just to give you a flavor of how things was at the time, this was a machine with 128 nodes, 2 processors each process a single core. and linked up by a 100-base T-switched network. And when I was a postdoc at the CFA, it often happened that one of these nodes would crash, and you would then go down to the cellar, rip out the blade out of the rack, and reboot it, and slam it back in, and continue the calculation. So this was how we did things at the time. It was fairly bare bones, but it was state of the art, and we could, for example, obtain predictions for the cosmic star formation rate density and its evolution as a function of time. And by separating the physics model and the numerical aspects, we could prove that there was a converged prediction. The physics model was clearly limited and not complete, but we managed to navigate around the numerical resolution limitations. And I do still think this approach is very much worthwhile even today to have a clear understanding of what would be a numerically converged answer for a set of partial differential equations you want to solve. That's your physics model, and once you have a definite answer, you can think about improving the physics later on. And this idea of connecting boxes of different scales, I mean, we still use this. For example, in Elastis TNG, we have, of course, these 3 box sizes, TNG 50, 100, and 300. Each of them can be used on different scales. The rare objects are only found in these large volumes, and if you need exquisite resolution, you turn to TNG 50, but you don't have very rare systems there, unfortunately. Now, also at the ITC, the first work originated that included black holes and their feedback effects in simulation of galaxy formation. This started from Tiziana Di Matteo, a postdoc fellow like myself at the CFA and then ITC, and I, together with Lars Hörnqvist, we thought about this problem and, of course, wanted to account for the substantial energy release that's coming out of black holes, which was known to be, by back-of-the-envelope estimates, to be comparable, at least, to the total amount of energy released by all supernovae combined. So clearly, energetically, AGN would always been could be suspected to be an important player in galaxy evolution. But at this time, 20 years ago, this was not something that was universally accepted at all. I mean, most observers were in denial that the black holes would influence galaxy evolution, I would say, at the time. We certainly got a lot of flack when proposing this. And what also was theoretically unclear is how the AGN energy couples to the gas in the first place. Still unclear, still a major research question in its own right. Now, we then devised a simple model where we introduced supermassive black holes in galaxies at their center, described accretion through Bondi accretion, simplest thing you can do, limited to the Eddington accretion rate. And then we conjectured that not all of the liberated bolometric luminosity would leave the galaxies, but a small fraction would locally heat the gas. And that's what we coded up and then did a numerical experiment, a kind of a hypothesis testing. That was actually also, for my own research career, a key experience, and suddenly seeing something that I was not quite expecting, because what happened in these galaxy collisions was that, yes, of course, the tidal forces drove gas into the nuclei, a starburst was fueled and triggered, black holes started growing from and accreting from this gas as well. They grew exponentially in mass. The energy output grew exponentially. And what then happened was that, of course, once things grow exponentially, eventually they have to stop. And here it stopped when the thermal energy drove a pressure-driven wind, expelling most of the gas from the remnant galaxy and leaving behind the dead red elliptical galaxy. And that was electrified us, and we thought we have identified the main channel for creating massive red galaxies. We thought for a while that this was a major merger would be always required to do this, and that quasars would then shut off star formation, would also shut off themselves in the process, being suicidal, and then leave behind these red dead galaxies. We now understand from our cosmological simulations that the picture is more complicated. Quenching occasionally happens in the small mode, but most often in different modes. But what this already showed, this feedback-regulated black hole growth, was that it explained correlations between the black hole mass and stellar properties quite nicely, explained the colors of dead galaxies. And so since then, black holes have become a key ingredient in galaxy formation to this very day. Of course, now the modern models are more sophisticated than this, but I think there are now a key ingredient, I think, that has been coming out of ITC and collaborations with the ITC. I want to also draw attention to another important thing that's sometimes overlooked a bit, but also the numerical accuracy of simulations has been recognized here at the ITC in work that I've been involved in also with Lars mostly. Namely that at 20 years ago, there was a time that these SPH codes were widely used for galaxy formation. And it turned out they didn't account self-consistently for the so-called variable smoothing lengths, for the adjustment in resolutions. And at low resolution, we could show that this is actually causing spurious excessive cooling. So that contributed to the cooling catastrophe. And we introduced a novel method that conserved entropy accurately, and also energy where adequate, where applicable, in isentropic parts of the flow, that means outside shocks. And what this then behaves well in the cooling, also at low resolution. And for us, the lessons here was learned that, okay, actually numerical accuracy might be a big factor. And another side thing that wasn't so apparent to us at the time was if we conserve entropy properly, everywhere outside of shocks, then we actually have a problem perhaps with mixing, because there is no source of mixing entropy. And that is really a problem became apparent some years later in this seminal paper by Oscar Argertz, where different codes applied to galaxy formation were tested on a problem where you blow a supersonic wind on a cold cloud, right? This is something that's, of course, happening in the ISM. And the outcome, the long-term outcome was decidedly different between the particle-based codes and the mesh codes. SPH codes retained some of the cloud material, and the mesh codes disrupted it completely. And this is ultimately due to low accuracy of the particle codes in the shearing layer, where the Kalman-Helmholtz instabilities and others are suppressed. But it's also because of the lack of entropy production in mixing regions, right? So there was basically a major design flaw in these methods. Myself, I was then using that as sort of starting point to devise a new idea to especially tailor towards the galaxy formation problem, namely creating a moving grid where you could use the accurate formulations of mesh-based hydrodynamics, but you would have still a quasi-Lagrangian following of the mass into galaxies, and so you get an automatic adjustment of the resolution where you need it. Inside the galaxies, as you see here in this Voronoi mesh that's used as a tessellation. And you also are able to sustain very high accuracy in highly supersonic flows, which is important in galaxy formation. So with this technique, there was then a lot of work at the ITC, in Lars Hönquist's group in particular, trying to figure out, is that an advantage or not for galaxy formation? And for example, here's a work by Mark Vogelsberger from this period, a good 10 years ago, where these two methods were applied to the same initial conditions. And on top, you see the galaxy, this galaxy forming with this moving mesh code, and at the bottom with this particle-based code. And right clearly, you see why, good news is there is a galaxy in both cases. It looks very different, though, for the mesh-based hydro. It is much better defined. It's bigger, and there's much less noise in the hydrodynamical fields. And the conclusion from this was, of course, that yes, actually, the numerical technique is potentially very important. And since then, in the field, there is a hotly debated topic. Is this something to worry about, given the fact that differences in physics parameterizations, in particular feedback process, can induce even bigger changes. And while this is true, sometimes, I think it's also important, these numerical accuracy issues are very important, and we see them in many different examples. I'll spare you the details. So I do think that, fortunately, we have this moving mesh technique, and that then formed the basis of these elasticity G calculations we already heard about, and I hope that Annalisa will probably expand on this further. And it's quite rewarding that these calculations we can now do about galaxy formation, which wasn't possible 20 years ago, and they produce somewhat realistic galaxies. I mean, in fact, it's stunning how many properties are basically matched. And the tensions, of course, tell us about where these physics models are in need of further improvement, and there are some. But the utility of the field, I think, is really very large, and as you see by the very large numbers of papers that have been written by many people and analyzing many aspects of that we, the actual people who simulate this in the first place, never had thought of, which is also great to see. Now, a few remarks about present. One aspect, for example, what you can do with these galaxy formation models is you can study, for example, a long debated question, what's the dependence of galaxies on environment? And there we have now very clear evidence that there is a fairly strong dependence. For example, if you compare galaxies found in dark matter halos of the same mass in voids and non-voids, then the void galaxies, they have lower stellar mass, quite substantially lower stellar mass. This is then direct evidence, for example, that simple HOD prescriptions are intrinsically inaccurate if they don't account for such effects, which they normally don't do. And you can then turn things around, for example, and ask, if galaxies of the same stellar mass, they have different formation histories if you look at voids or non-voids? The answer is yeah, they do, of course. They have then to grow in voids, they have to sit in larger dark matter halos. Turns out their metallicity is lower, but their gas metallicity is higher because they have deeper potential wells to retain more of the metals, and they're also substantially younger. This just serves the point that without these type of detailed galaxy formation models, we probably wouldn't know about that, because the simple theory assumption is still that galaxy properties in a halo depend only on halo mass, and there's now plenty of evidence that this is not true. We can also use these simulations to zoom in on, for example, filaments between halos. The zoom-in technique is often applied to individual halos, and we learn about the galaxy in them. But we now also we use that to learn more about the IGM and, for example, thin filaments connecting halos. Here's a nice recent paper by Sam Liu, a student of Near Mandelker, where this was done zooming in on a filament connecting two massive halos at redshifts of around 2.4. And the white regions here, you see, this was selected for an analysis to look at the detailed thermodynamic structure of these filaments. And when analyzing this with high resolution, one can then really understand how the gas, for example, makes it into filaments. You see the outer accretion shocks that give rise to an outer thermal zone. You then see once the gas starts cooling, develops a turbulent inflow region, which here is called the intermediate vortex zone. And in the inner parts of the filament, you have an isothermal core. That's the stream of gas that then in the direction of the filament penetrates into the CGM and feeds galaxies. So we can use these hydrodynamical simulations to understand this better and discover things. For example, here a quadrupolar flow pattern was found, that the gas in the filament has an interesting peculiar flow pattern. If you stack many of them, you see that, because the sheets that feed the filament are slightly offset from the center and basically set this gas into motion and impose over the turbulence an interesting quadrupolar flow pattern. So sometimes you can discover things in these simulations that you don't necessarily would have expected maybe in the first place. Now, in recent times, we also tried to push these calculations to larger volume, because one area where they're really needed is for cosmology. We have these very large missions, Euclid, DESI, LSST, that try to look for cracks in the standard cosmological model. And there is now already tantalizing evidence. Maybe we'll soon see that the lambda in the lambda CDM model is convincingly ruled out. We'll have to see that. But for supporting these interpretation of the data, you need much larger theoretical models. And recently we've produced these Millennium TNG simulations, again, a project where the ITC is critically important. And I've done this mostly with the ITC group. And Sonak Bose, who is here, was also at the ITC still at the time. So we've combined their Elastus TNG and Millennium, and in the sense that there's a 500 megaparsec box size where we wanted to have a hydrodynamical simulation model like Illustris TNG, and compare that to a high resolution dark matter model. So that is 15 times more volume than TNG 300. But then we produced still larger simulations with more than 1 trillion particles, 1,000 times the volume of TNG 300 now with 3 gigaparsec sidelings. And these are the volumes we really need to compare to the clustering statistics and the weak lensing statistics that are now the result of these very large mega surveys that are done currently. We also included massive neutrinos. This has become another important, interesting goal of these large surveys, because they can actually, turns out they can constrain an important particle physics unknown. What is the summed mass of the light neutrino species? And so we've run this with 100 millielectron volt summed mass. And then you can get predictions. For example, you can make galaxy surveys, artificial ones, that also contains hundreds of millions of galaxies. This is a past light cone here from us to redshift of 2 with a few enlargements. So you see here the cosmic large-scale structure, of course. This was without the redshift space distortions. And here you see also the neutrino field on top. So again, we sit here at the center, the reddish down you see the dark matter, and on top is the neutrino density field. And what you see from this picture is that out to redshift 2, left and right, the neutrinos are still super smooth. But as time goes by, they continue to become non-relativistic and eventually respond to the biggest cosmic structures and start to cluster in them and amplify the clustering at late times. And this is a time-dependent process where you basically have a kind of a step function feature in the power spectrum that, if detected, can tell you about the neutrino mass. So that's the interesting cosmological angle. And we are in the process of trying to make theory forecasts for this. You also get weak lensing and the baryon impact on this. And what's interesting is that here you see the angular power spectrum of the weak lensing shear convergence. They are in the green and yellow line, for example, you have 2 hydrodynamical simulation models, our Millennium T/Elasticity G and Horizon HN, they kind of agree. Other hydro simulations predict even larger impacts, baryonic impacts on this weak lensing power spectrum, even at an L over 1,000. Flamingo and also Bahamas, and they invoke even stronger HN feedback. So that's unclear at the moment yet what the strong impact is. But you see that as blue line here, that's the impact from the neutrinos. It's the same order of magnitude. And so you need to understand both of these effects accurately to avoid that you're biased by the systematics due to this. We also used these simulations to, for the first time, measure intrinsic alignment signals for weak gravitation lensing. It's one of the most important systematics there. And it's also based on very primitive theory so far, mostly on perturbation theory. But now we can measure the galaxy shapes directly in sufficiently large volumes to measure the shape alignments of the galaxies. And previous looks for this have largely failed because the hydro simulations were too small. But now with Millennium TNG, we could do this. And Ana Maria Delgado here at the ITC has done, I think, produced a groundbreaking detection of that signal. We see the intrinsic alignment here in orange for elliptical galaxies with incredibly high signal to noise, both in the 1 halo regime and the 2 halo regime out to beyond 100 megaparsec distances. So that's really, I think, very important. We also find weaker signals for spirals as well. So yeah, that's something that I think will be very important to improve current parameterizations for weak lensing in these large surveys. Now, finally, let me make a few remarks just at the end on the future of these types of simulations. Of course, there are important physics challenges that we would like to address in the next couple of years. There's a long shopping list. Let me just spell out a few of these things, but you could, of course, continue this. One very obvious thing is that we would like to simulate large galaxies with resolved interstellar medium. That is, huge progress has been happened there by several research groups doing this for small galaxies, in particular, dwarf galaxies, where you can already reach this 1 solar mass resolution, give or take. Soon, I think we'll be able to do this for big galaxies, like Milky Way-sized galaxies, which we are not yet able to do. And once we have that, then I think we'll be able to really see whether we understand the physics that drives galactic winds and outflows, which I think is currently really is not the case. And even though, we assume very strong outflows because that's what's needed to explain galaxy formation in lambda CDM. It may well be that our detailed models will not produce those, which would be a big crisis, I think, for our theoretical understanding for galaxy formation. I think it's going to be interesting in the next years. Of course, we are working on radiative transfer and improving the spatial dynamic range close to black holes. It's all pretty difficult numerically. And also in trying to get better orbits of black holes, for example, to then forecast better for missions like LISA in the future, what event rates of mergers, supermassive black holes can be expected. So I think for that also these future galaxy formation simulations will be instrumental. Frontier, I just want to say something about, we could already do this now if we were able to use biggest supercomputers. This is the biggest, fastest one currently, Frontier in the US, exascale machine. The problem with these exascale computers is they are very difficult to use. They now rely on GPUs. This is a diagram that illustrates a node there. It has 64 standard cores, but the bunch of the floating point performance comes from 8 GPUs sitting in each of these nodes. And so each of these nodes can then have a concurrency of about 56,000 threads. So you have to somehow find a way to make use of this concurrency for tightly coupled physics problems. And that's actually a major headache. And so, I think, and, also in Europe, we have LumiG, which is 3 times smaller, but the same architecture, but we would really urgently like to use this machine. But it's difficult. Now, let me finish with this slide, which I use sometimes to liken the similarity of a big simulation code to an instrument that you put on a telescope, right? We build telescopes and we invest a lot of money to build sophisticated instruments, because without that, you couldn't use the telescope. We have very expensive supercomputers, and on that, you would want to put the code, which is kind of your instrument. And just to illustrate, this is also getting really complex. Let me give you a bit more history. In 2001, when I was a postdoc at the CFA, I published the Gadget 1 code. It had 8,000 lines of code. Now, 2005, this became the Gadget 2 code, had 18,000 lines. 2010 became 160,000 lines, became a repo. When we did Illustris TNG, we had a repo with 332,000 lines of code. And at the moment, we have a repo 2 in the making, has already 480,000 lines of code. Now, the problem with this is that to write 500,000 lines of code, a single person needs more than 30 years of work. So this is unfortunately not something the graduate student can do anymore. But the field is still working like this. We're still expecting that single graduate students are able to manage these codes and improve them. We don't have any professional support, unlike instrument builders who have a machine shop and a whole army of engineers usually. So we have none of that for our large code. So I don't think this is sustainable in the long run to operate these very large supercomputers. So yeah, and I leave you with my summary. Thanks.
So Volker, you remind me of the people back in the 19th century that were very worried, especially in London, that if you extrapolate the number of horse carriages that were used, there would be too much poop filling up the streets. And then the car came along. So with your concern about the number of lines of codes, now we have ChatGPT writing codes. Mm-hmm. So do you think that artificial intelligence would substitute for natural intelligence in the coming years? Because it's already getting there. And obviously that will solve your issue with the number of lines.
Yeah, I'm not worried about that.
Okay, second point. If you didn't notice, Erika put a hook for you in the first talk, which was theory doesn't agree with data about the highest redshift galaxies. We will not let you off the hook. You didn't say anything about that. Are you worried that something is wrong with the standard model?
I'm not worried. I would say I'm excited about that. So I think it would be, that's what we wanted. I mean, we wanted, in theory, I think we were a bit desperate that everything was falling into places. And now Hubble tension is 8 tension. You have plus, the early galaxies we don't quite understand. It's I think means that we have to go back to think harder, and that's what and the prospect to discover something new, I find this exciting. I'm not worried about this. These are theory models. They have worked better than I expected, especially for elastocystine G. So I think it's good that we have all of this new input. And what totally surprised me, Arias' comment that observations were lacking behind theory. I've never heard this comment by anyone. But great, thanks. This was
is your gut feeling that the solution would be in the astrophysics or fundamental physics?
For the astrophysics, I would say the early galaxy growth. I do believe that the early galaxy growth there are various theoretical suggestions apart from things you mentioned earlier that could be explained, that the feedback regulated star formation, for example, the star formation proceeds much faster, that the IMF is very different and so on. There are a whole lot of potential theory explanations why galaxy formation at this early epoch is proceeding slightly differently. Mind you that our default assumption has always been everything we calibrated on today's universe applies the very same way at the early, that's the default assumption, which is, I think, reasonable. But maybe the conditions are so extreme, so different that extrapolation becomes invalid. And I think that strikes me as pretty natural. So without all of these other cosmological issues, we also have, I think, for example, the origin of supermassive black holes, I find harder to understand than, say, big stellar masses that appear more rapidly. That I think I can see that there might be solutions for this, but don't quote me on that. So
we will not quote you, but there are cameras.
Oh, okay. Yeah,
questions from the audience, please go ahead. In the back.
I have a simple question. So when you calculate in your code the gravitational interaction between 2 points at a distance, do you take the time delay into account? If no, why? If yes, in what way?
Yeah, you're referring basically, why can you do this in Newtonian gravity, even though you have gigaparsec distances, etc. So it's done like that, but it's okay. You could do the same calculation in general relativity, which would then on large scales you would get perturbation theory in general relativity. By lucky coincidence in nature, the results agree. So when you are computing based with Newtonian gravity, the growth of large modes, they grow with the correct rate, unless the modes are outside the horizon, so there are small corrections there. If they're inside the horizon, that works without retardation. The reason is basically that these scales are still linear, where this would matter. And in this linear growth, this Newtonian treatment agrees. Once you are once you become nonlinear, you're on small enough scales that Newtonian gravity is again fine. The time delay effects are negligible there. Again, up to basically close into relativistic objects, where then the curvature, where the Newtonian gravity is not good enough. But there have been studies where people simulated this in full GR on very large scales, and to their disappointment, never found really significant discrepancies. It's all agreeing pretty much to 10 to the minus 6.
One last question. Charlie, go ahead.
So, with the repo, you brought us really, I think, dramatic improvement on the methodological side to how this works. Do you see a similar transformation happening in the next decade or so in terms of not just more cores and more lines of code, but a smarter approach to problems, maybe faster and more accurate?
Hard to say. I hope so. I think there are, other techniques that are also, for example, we thought about discontinuous Galerkin hydrodynamics, which has a much faster convergence rate. The problem is with so-called high-order methods, which applied mathematicians would favor as a more efficient and accurate way. The problem here is that the coupling with other types of astrophysics would have to do everything at much higher order to have this benefit of faster convergence rate. So that's why at the moment I'm pessimistic that this will change much. I do think that in terms of, question is what's your goal? In terms of, we know basically how to compute gravity and how to compute hydrodynamics. And there are many different and very good codes around. They're all basically agreeing on the important problems. What's critically important is how can we actually use the challenge of parallelization is the real issue here. And I think progress in how to parallelize that on 500 million threads, that's what Frontier has, If you have all the GPU threads, right, you would like to keep 500 million computation threads busy on an interesting problem simultaneously. That's what we are not capable of doing. If we could, then we could do mind-blowingly super cool simulations right now already at the moment. I think we can do this for more simplified models, unique grid turbulence and so on. But the really multi-scale, multi-physics problems, this is really hard computationally, and parallelizing those problems, that's the challenge. The basic solvers we understand, but the parallelization problem, I think there's a lot of progress possible.
And we should all keep in mind that we still don't know what the dark matter is. And if we knew, that would help you quite a bit.
Yeah, right. We simulate alternatives to dark matter too, trying to, see as IDM, fuzzy dark matter and so on, for example. Also alternatives to the gravity theory, right? F of R gravity. We do things like that. The problem with lambda CDM, coming back to your question, is working so well, there was little motivation to really push further, right?
Well, yeah, there are still tensions, but anyway, let's thank Volker.